Okay, we're looking at a switching regulator explanation here. As you can see on the right side and on the left side, what we're going to do is we're actually going to take this and run it on a SPICE application. So as we introduce the circuits on the right, we will be moving over to the left and looking at how they operate. How they operate. I am Scott Duty, by the way, and I'm a 30-year power electronics expert, and I design both buck and boost regulators, which are what we will be addressing today. So this is about a client request to look at a step-down buck regulator, switching regulator. I was given these two schematics. On the right, you see the buck regulator. On the left, you see the LT1170 configured as a boost regulator. And the associated data sheets are given here. This third bullet was actually just for a software that I was going to look at to do better recording on my screen. So it's irrelevant to this discussion. Let's go over here. You can see the buck regulator. The request basically was just to figure out how the power flow works in the regulator. And you can see here you put in 10 to 40 volts on the left side. It goes through an integrated circuit and then an LC filter, and it comes out to the right side. And the whole idea here is to regulate the output voltage at the set current of 5 amps. How do you do that? We use what's called the switch mode power supply. The switch mode power supply has 4 basic elements: an output capacitor, an inductor, which can be located anywhere in relation to the switch, in this here rectifier. So the main power path is very simple in this. You turn the switch on, which is also going to be referred to as a transistor, but it's an integrated switch in this case of this particular integrated circuit. Turn the switch on, it puts a voltage at this point, so you now have a voltage across your inductor and the current flows to the output. Now, the best way to look at these circuits is once the output is at what we call steady state. So if we were to assume this was at 5 volts, we'd have a much easier method of understanding this converter. When that happens, you're going to have a higher voltage here to a lower voltage here. So the input voltage is going to be anywhere from 10 to 40 volts. It will be stepped down, or if you will, buck regulator bucked down to 5 volts. How? You turn on the switch, you have a voltage here that's higher than here because the input voltage is higher than the output. The inductor current starts to ramp up. Why does it ramp up? Well, it ramps up actually in a linear fashion because of the ratio of these components. If they were at a certain ratio, you would actually get a circuit here that would look more like an oscillation. But due to the fact that this is a very stiff and regulated high capacitance area, then you actually get the inductor current ramping up because you get V equals L di dt, the voltage across here, L di dt, instead of a resonance between these two. So we will see that. We will see how the square waves come in and how the ramps come in as more linear than oscillatory in nature. So if we zoom out a little, we come over here and we want to look at our boost regulator. What we actually have in this boost regulator is pretty simple. We have another topology, same set of deals. We have a very stiff output capacitor. We have a switch. We have an inductor, and we have a rectifier. Now, in this case, when you turn the switch on, essentially what it does is it grounds this point. So you get the input voltage across the inductor. When you turn the inductor off, this inductor current is going to want to keep flowing, and the inductor actually swaps voltage to make that happen. When you apply a voltage, it will keep that voltage across itself, but when you let go of that voltage, it actually calls what flies back. So it actually negates voltage. So all of a sudden, this point becomes higher than this point. So it will actually turn this diode on, and therefore it clamps at this voltage. So now you have 0 because, you have the input voltage clamped across here minus the output voltage. So you have 5 minus 0, or minus 12, and you have a negative voltage here. Whereas when you have the switch on, you have a positive voltage. So that's how they differ. We'll just look into the converters themselves. So if we go to our first slide, what we really want to do is we want to take this regulator and we want to put it into a spice file, because that's going to tell us everything we need to know. So we will look at the main power paths, the output voltage, the inductor current, the switch voltage, and the diode current. And that will explain all the concepts I just talked about how switch mode power supplies work. We also look at some secondary paths. I didn't mention those, but they are in the schematic. And essentially there is a divider network here. All this is a reference for the output voltage that's divided down to match what the internal reference is of the converter. Usually they hang out at 1, 2.5, or some reference voltage there. And then the only other really noticeable component here, this is the AC compensation. All that really does is it determines how stable the circuit is. In other words, it won't oscillate, but it also determines how fast it responds to a transient. So if we look at this, we have secondary power paths of the divider voltage, the control voltage. There's also a limit and a shutdown pin on here, and you can see those that they come out. All this really does is, because it's got a bar here, it says if I'm low, I shut the circuit down, or I have a programmable current limit so that I don't damage my switch in here. So these are preset. The current limit is 6 amps. We never reached that. So in the main power path that was requested to this customer, we're really not going to get into any of the side circuits other than that. So if we look at the power flow in the buck regulator, as I mentioned, we want to look at the output voltage. Very simple to do. We just look at the buck schematic. You can see it comes up here, and what we want to do is just simulate. So this is called run. So if you go over this one little thing here where the guy's running, you get run, and in 2 milliseconds an analysis pops out. Well, we want to look at the output voltage, so we would hover over this point. Our cursor turns to a probe, and we see that the output voltage took some time to ramp up. There was a delay in starting the circuit, and then there was a little bit of an overshoot. The control loop kicks in, and we get steady state. Okay, so that is depicted here. We say we get steady state here, about 0.9 milliseconds. Well, let's go out and let's expand this part of the curve and see what we get in order to figure out what's really going on here. So if we look at this and we hover over our output from our spice file, we can just start to zoom in on what's going on here. Okay, and we want to really look at what's happening on the output. So you can see that this has an average of about 5.12 volts out, and then it has some associated ripple that's triangular in nature. Now here I've set the actual limits of 1.9 to 2 milliseconds, when in actuality we're looking at 1.94. If I wanted to change that, I hover over this axis, I get a ruler, I say I want manual limits. You can tell it's going to 1.94. I change that to 1.9 by in this field right here. Boom. Okay, but we want to know what the source of that is, and so we actually have our main power path here explains that. So if we go out and we say, okay, I've got an inductor here, I want to look at the inductor current, I want to see how it relates. So we would go out here, we'd say add trace. What do we want to add the trace of? IL1. I is current, V is voltage. So I, the current through here, actually maps right over the voltage. But we can see here that it's peak to peak current. Okay? So it goes from 0.56 to 1.44. Okay? And it centers about 1 amp. So this is in the continuous mode. Why? The inductor current never drops to 0. It only drops 0.56 amps. If it were to drop to 0, this converter would still regulate. The only problem is this capacitor would have to pick up the current during the off time. So in other words, this would fall to 0 and then it'd be an off time before the next cycle switched on. We could easily look at that if we wanted to. However, right now we're looking at continuous mode, at a current that keeps us in continuous mode, a load current through this resistor, and we understand that that's going to tell us most of our theme, because people like to operate these in continuous current mode and keep this ripple as low as possible. As you can see here, it's already 1 amp peak to peak. But what's really important is how much ripple does it put on the output. So continuous mode conduction for this is best, because essentially what you do is you shrink that peak to peak. So we want to go out and we want to say, okay, I want to look at this switch waveform, which is the next thing I say, the switch current, and I want to figure out how this inductor comes together. So we go off and we say we want to add a trace. And the trace actually is ISW. And we get this trace and we say, okay, what's that? Well, what happens is it's really looking at the current into this node. Okay, so it assumes positive is into the node. We actually want to look at the current, how it contributes out to the inductor. So we're going to cut that, right click, delete the trace. We're going to go back in. We're going to add the trace, okay, but we're going to say we want the opposite polarity, minus IX UW1.SW. Put that in there, and all of a sudden we get a little bit more information about what's going on. As a matter of fact, as you can see from the red trace here, the transistor current is actually the upslope of the inductor current. Why is that? Well, let's look at this next trace. If we look at the switch voltage on that node, we will understand how a buck regulator works. We want to add a trace, and we want to look at, I think it's node number 1. Let's save ourselves any question of having to look at that by just placing a probe there, okay? So voltage probes are very easy to place, okay? And lo and behold, it is node number 1. But here's what's happening. That node is flying up to 18 volts. Again, we're putting 20 in, so there's a 2-volt drop here we're not accounting for. But look at what's happening. It's flying back to minus 2 volts, or 1.5 volt. So this waveform is oscillating, and it turns out is the area under this curve is equal to area under this curve in volts seconds. So the amount of volts and the time you apply it has to be equal in order for this converter to be stable. Another thing we know is voltage across an inductor creates a change in current. V equals L di dt. So when this switch is on, this voltage is going to rise up because this voltage is higher than this one. And you're going to get a positive slope in the inductor current equal to the voltage differential from here to here. And it's going to be times the inductance value and divided by the amount of time that this takes to transfer here. So V equals L di dt. So we can look at this di and we can actually calculate it. Alright? Now, so we know how the voltage relates. We know how the voltage relates to the transistor current, the switch voltage. We know how the transistor current relates to the inductor current. We know how the inductor current relates to the ripple. Let's go out and look at this diode and see what happens, okay? So if we add the trace for the diode, it would be I, which is current, to D1, which is the diode. And we can see that we got a new trace here. ID1 is purple, and it's overlaying on the downslope of the inductor current, okay? So what we've essentially done here is we've taken this current as a sum of this current through the diode and this current out of the switch. And that makes sense. Now, as far as the power path goes, we can look at some other things here. We want to look at the secondary voltages on these little devices here. So we want to get rid of all the traces except for the ripple. So let's get rid of all these traces. Delete this trace, delete this trace, delete this trace. Okay, so we got the output voltage. And we can see that it's very small, okay? So let's just see what happens when we put a probe right here. So it changes to a probe. Oh, you can see it's about 2.1 volts, whereas this is somewhere around 5 volts. If you want to measure them directly, all you do is you say, alright, I want the output voltage. I right-click on it. I want to put a cursor on it. Awesome. A cursor comes up and says, you know, you're about at 5.12 volts. Great. What about this guy? Go out and I'll say, you know, I think I'll put cursor number 2 on him. Awesome. Okay? So cursor number 2 is now tied to V3, and you see it's about 2.2 volts. Well, that's actually the ratio of these resistors. So if you took the output voltage times this value, divide the sum of these two resistors, you get 2.1 volts. Okay? So cursor 1 represents 5.112. That's this upper trace, and that's this V out. Cursor 2 represents 2.589, and that's this lower trace, and it's about 2.2 volts, and it's the divided ratio of these resistors. We're not worried about anything horizontal, just the vertical values at this point. So let's go to our next slide. Oh, what happened here? Well, we changed our input voltage from 20 volts to 10 volts. And all this really does is it tells you how the duty cycle in the inductor current will actually change. And so let's look at that. You can see here that the duty cycle goes up. Let's zoom in. And it gives you the gain of the converter. So continuous mode operation. Again, this does not fall to 0 in the inductor current. In the first case, you get a 20% duty cycle. The second case, you get a 62% duty cycle. It should compute exactly to Vn over V out. I'm sorry, V out over Vn should equal this number. However, we have a drop in voltage across the input switch. And so that's why this is not exactly 50%. 5 divided 10 would be 50%. But when you take in the inductor, the drop across the switch, the converter makes up for it because its whole idea is to regulate this output voltage. So the input voltage is not being transferred here. There's a drop that's being accounted for. That's all you're seeing. It's nothing big. Now, we jump over to the boost converter, and we can look at this topology. Let's play the same game. Okay, we go out with the boost converter, and we say, look, what we want to do is we want to create a boost converter that looks like our schematic, and we want to look at the same essential power outputs information. Great. Get it? Do our run. Notice it takes a little while to complete the run, but we don't care anyway because we haven't really chose our output. Oh, there's our voltage. Looks like our waveform. Now this guy's taken 20 milliseconds to settle out, so we're going to look down here because we really want to just amplify this output voltage and see why it's not a pure DC value. Again, we get ripple. Now we got some ripple here, and we can do a peak to peak. If we look at this and we right click, we can just take those two cursors, first and second, and we can say, alright, we want to look at the difference across here. Okay? Pretty easy to do. You put this one at the top, you grab the second one, which is, oh, it's not grabbing it. Grab the second one, you move it to the bottom. The difference between the white lines and the dotted lines is about 190 millivolts, and I've written in here, yeah, it's about 192 millivolts peak to peak ripple. Alright, so that's about 1% of the 12 volts. It's not even 1%. Well, it's a little over 1%, almost 2%. So that's not bad ripple. Let's play the same game we did before, okay? What was that game? Well, let's look at what's going on here with the different currents, okay? So again, let's see how the inductor current stacks up to this. We want to add the trace of L1. I is current. We grab I and we say, what does it look like? Well, first of all, it gives us a right-hand scale, so we compare current to voltage. And you can see that that ripple is just based on the downslope. Well, that makes sense because here's the diode. The inductor is being chopped on and off. So you're really only getting this diode current, and that's why your ripple looks like it does. How can we verify that? We add a trace. We say we want to look at the diode current, and we can see that that pedestal, the diode current, even though it's a much larger 4 amp scale than this small voltage scale, it pretty much steps over the ripple. Now where's that ripple coming from? Well, really what it is it's AC current that's going through our output capacitor. There's a little ESR here. It's an equivalent series resistance. It's not even in the schematic, but it's, if you right click and look at the component, you can see you've got 50 milliohms of resistance here. And that is actually taking the AC current, because the DC current is going to go through the load, so the AC current is going to make a ripple voltage here. What does it look like? We go, okay, we want to look at the current through the capacitor. That happens to be capacitor C1. Lo and behold, IC1 is, it's IC2. We got to cut this guy out, so we hit him, delete the trace, and we say we want to add IC2. So we add the I, which is the current of C2, and lo and behold, it looks just like this. And you can see where your ripple current is coming from. It's almost exactly peak to peak with the ripple voltage. Now the only other thing we haven't done here is to add the transistor current. So we're going to say, oh, let's go look at the switch current. Okay, add trace. It's actually the switch current here. Now notice we don't have to play that game of inverting it like we did with the buck regulator. Why? Because the current is going into the pin. When this turns on, it actually takes and pulls current to ground because the switch is referenced to ground. How do we know that? We go back over here. We say pull up our schematic. You can see right here that this takes switch to ground every time it turns on. Now we're happy. We know how a boost regulator works. Okay? How do we know it? Well, we just go out and we cut off all these traces, and we have the inductor current, the output voltage, and the switch current. Well, let's just go out and see what that V switch is doing. We add the trace of BSW. Again, we don't know what node it is, so all we do is we take a convenient little pass over, and then this turns into a probe, and lo and behold, again, it's switching between 0 volts and a total of 13 volts, which on the input here. And so, well, wait a minute, what's it switching to? Yeah, VN, and it's going up to about 13 volts. So we see that we have an oscillation going on here, and what happens is the volt seconds that you apply have to be equal to the volt seconds when it clamps and turns off, and that's how the inductor works. So this doesn't actually, this reference is 0, but you have plus minus on, and then when this goes on, this flies high. When the switch turns off, you have plus minus voltage across here. So you have plus minus here, turn on. That's the positive direction. Current ramps up. But see, this, when you turn off, okay, what's going to happen, you turn the switch off, is this point's going to fly up because the inductor reverses its voltage, and it'll clamp at the output. So you actually have a higher output than an input, so you'll have a positive to negative voltage here, and the volt seconds across the inductor should cancel out, and you have nice steady state operation. Finally, what we're doing here is we're saying, okay, what is the output current in relation to the input current, or in relation to the inductor current? So we get rid of a couple traces, and we say, okay, we know we have an inductor current, but we also have a load current. What's our load current in relation to the inductor current? And we say, well, let's look through the current through IR load. Oh, it's way down here, okay? And our inductor current's way up here. So what is that really? Well, what that really is you can see that the current goes from 0.29 to 0.4 or to 0.9 amps, okay? So the load current is actually just a small percentage of that. It's down here at 1 amp. So it's actually the average diode current. It's the average of this current right here in the diode, okay? So what we're doing wrong here is we're looking at V out, okay? Let's look at the diode current compared to the output current, and then it becomes apparent how this circuit works, okay? So it's actually the average of this current, the on time of the diode, okay? Now if you do the same thing with a buck regulator, you're going to find out that that current is the average of the inductor current. Why? Because the inductor current is the output element, not the diode. All right. So that's just the difference. What does that mean? Well, what it means is you really have to kind of filter this point, okay? So in other words, you want to take and you want to filter the inductor. The same thing is going to happen here in terms of the buck regulator with these secondary components. This is just going to divide down the output, and then this network here on the BC is just going to determine the AC compensation. Those are both small signal. We're dealing with large signal power flow here, so we're going to stick with that. Now, if you go to the next slide, you see here that I have done a comparison for you, rather than pull up the buck regulator again, but you can actually tell what's going on here. See the inductor current versus the load current with the buck regulator? It's the average current of this element. So it's actually the halfway of the triangular wave, whereas it's the half on the output current on the boost regulator. It's actually the average of the current in the diode. And so again, we need to take this and filter it. Okay. For some reason, I jumped to the boost converter gain. We're going to skip this slide, and we're going to go back, and we're going to look at filtering. Okay, I apologize. I didn't look at the filter, and that's what I should have done. So what I wanted to do was establish, okay, yeah, this has got a much rougher peak-to-peak output voltage. Well, how do we fix that? Well, in the schematic, all they do is they put in a filter. So we have ourselves another converter with a filter on it. So we've taken the filter that was optional in the original schematic, and we put it in here. So all we have to do now is we have to run that. Let's just take our bar and try to stick it back up here so it doesn't get in our way. We're going to do the same thing again, put a probe here on the output. We can see it's settling out. We're going to zoom in on that current because we want to look at how radical it is. And there's your ripple current at this point on output. Now what happens when we put a probe over here? Wow, look what happened. That current actually just went right down. How do I know? Because I got rid of my second probe, and now it's not going to put two on there. But you can see that when I probe over here, the current has been filtered greatly, and that's because this filter here rejects this frequency. And so that's how you take the choppy output current of the buck regulator and you put a filter on there. Now these boost regulators, actually you can take advantage of that input current, and that's what power factor correction does, and you can shape the input current, because now this input current is going to be the average of that level triangular. So that's how power factor correction works. They align the current with the voltage, and they get a good power factor. Okay, now we're on our final slides here. What we want to do, we've looked at all this. Oh, so let's look at the duty cycle of the continuous mode operation of the buck. And all we do here is we change the input voltage, and we notice that the duty cycle changes. So when it's 5 volts, the duty cycle, it's on much longer. It's on 65% of the time. Okay. Well, I'm sorry, for a boost converter, it's on 65% of the time. And then for 10 volts, it's only on 20.9% of the time. The reason for that is the gain is the duty cycle, which is in the denominator of the gain equation, and this is in the continuous mode. So continuous mode operation, you have 65% on time. You divide by 1 minus 65%, and you get a longer on time. When you up it to 10 volts, you actually drop the input on-time duty cycle, which is just the relationship of this to the overall waveform. Okay, so how do we look at duty cycle? It's pretty easy. We just go like this. We come out here and we say, alright, I want to look at the on-time of my switch versus the off-time. So we're going to cut all our traces, delete this trace, delete this trace, and we come out and we say, we want to look at the switch. Okay, well, how long is that switch on? Pretty easy to do. From here, blow up the waveform so that we get one cycle. Pull up our cursors. Okay, and you can see here that we want to add 2 cursors. Okay, because we want to measure between 2 different points. So these are actually two cursors laying over each other. We take number 1, we say, okay, you start here. We take number 2, and we say, you start here. That's one complete cycle. Frequency 100 kilohertz. Great, that's right here. Horizontal is 10 microseconds. Okay, so a period is 10 microseconds. So the on time would be the percentage, would be this pulse. So that's 3 microseconds. So if we take 3 over 10, we're on for essentially 30% of the time. And that's if our input voltage is 5 volts. And so our gain actually is 65.8% here when that happens, when we're 5 volts. That's pretty much an explanation of what's going on with the converter. I'm going to end the video now.